Hey guys, welcome back. This is William. Today I want to start talking about the divide and conquer paradigm we often see in recursive programming. Divide and conquer is a way to simplify a problem by breaking it down into smaller, more manageable subproblems. It is based on the idea that solving these smaller subproblems independently and then combining their solutions can lead to the overall solution of the original problem. It's a technique that we see used all over the recursion landscape, including sorting algorithms like merge sort and quicksort, in the search algorithm space like binary search, and in many other algorithmic problems that exhibit overlapping subproblems. In the last video, we looked at how to find the maximum element and its index by iterating through a list recursively, checking each element one at a time. While this certainly is one way of solving problems recursively, it's not very different from a traditional loop structure, if you think about it. Today we're going to begin looking at a more interesting way of solving these recursive problems by using divide and conquer paradigm. Let's rethink of how we can solve finding the maximum element in a list. Instead of going through the array left to right like we did previously, instead, we're going to be breaking this problem down to smaller and simpler subproblems. Recall that our original goal is to find the maximum number in a list. Notice that if we split the array into a left and a right component, that finding the maximum of the left and the right array equals the maximum of the whole array. This is important to note because it means that splitting up the array to find the maximum will not change the value of the true maximum of the whole array. After we split the original list into two parts, we can further split the lists again into 4 lists, and then split those 4 lists into 8 lists composed of individual elements. Now, going back to the original problem we're trying to solve, which is finding the maximum element, we know we can combine 2 lists of numbers together to find the maximum of those 2 lists. We also trivially know that the maximum element in a list with a single value is the value itself. With this information, we can begin finding the maximum value of the entire list by working our way upwards. Let's begin combining lists together on the lower left, starting with 2 and 1. The max of 2 and 1 is 2, so we can return 2 as the maximum value. Then we take the max of 0 and -4, which is 0. Then the max of 3 and 6. And 7 and 5. After that, we can reapply the same process to the third row. The max of 2 and 0 is 2. So we place 2 as the maximum value for that sublist. And then the max of 6 and 7 is 7. So 7 becomes the max value of the right sublist. Then we reapply the same process for the final 2 sublists. The max of 2 and 7 is 7. And in the end, 7 is the maximum element in the list. This process that we just saw of breaking down a problem into simpler subproblems and then solving those subproblems is what we call divide and conquer. Awesome. Now let's take a glance at how the divide and conquer algorithm for finding the maximum element is implemented. You'll see that we're repeatedly splitting the current segment based on the interval from I to j at some midpoint. However, before we run through this code in detail, I want to illustrate how the division of the segments takes place because it might not be so obvious. Let's imagine we have a given list and our objective is to divide it into smaller lists. To accomplish this, we maintain a record of the indices representing the segments of the list as we progress down the tree. This approach enables us to keep track of the specific portions of the list that we're working on, eliminating the need to create a copy of the segment itself. So highlighted in blue are the indices representing the initial segment. I represents the left index of the segment and j represents the right index of the segment. When splitting the segment 0 to 3, we find the midpoint by adding indices I and j and dividing the sum by 2 The midpoint position allows us to compute the new indices for the left and the right segments. In the given scenario, the midpoint is at index 1, resulting in the left segment being 0 to 1, and the right segment being 2 to 3. We can reapply the same process to split the left segment again. In this case, the midpoint is at index 0, and the new left segment is at 0, 0, and the right segment between 1 and 1, both inclusive. And similarly for the right segment. Here the interval 2 to 3 gets broken down into a left segment of 2, 2, and a right segment of 3 to 3. And that's how the splitting process works in a nutshell. Now let's go back to the pseudocode for a moment. Now looking at the code again, you can see that inside the find maximum element function, the first thing we do is check if the list is empty and return null if there are no elements. The reason for doing this is that there's no way to divide up an empty array any further, so immediately handle this edge case. It also prevents us from having a negative index value on the next line, which would cause the recursion to spiral into a Stack Overflow error. On the next line, you can see that we're calling the findMax function below, which is what actually finds the maximum. The input to this function takes two indices, I and j, which represent the segment of the array which we want to find the maximum for. Index I is the left endpoint and j is the right endpoint. Since we want to find the maximum of the whole array, we pass in I equals 0 as the leftmost index and j equals the length of the array minus 1 as the rightmost index. Now let's take a look at what exactly is happening inside the findMax function. The first thing we do is check if I is equal to j, which means that the size of the segment or interval is a single element. Since we know that the maximum value for a single element is the element itself, we simply return the element at that index. And this constitutes our base case. Next, in order to split the segment in half, we need to find the middle index position between I and j. This allows us to split the current segment into two parts, a left segment from I to the midpoint and a right segment from the midpoint to j. Then on the next line, you can see that this is where we do both the segment split and then the combination of segments on the callback. The first findMax function call corresponds to the left segment and the second call to the right segment. Since the indices for the segments is inclusive, the left segment ranges I to mid, but to avoid an overlap, the right segment starts at mid plus 1 and ends at j. And that's how you use divide and conquer to find the maximum element in a list. Alright, so we just finished taking a look at how to use divide and conquer to find the maximum element in a list. The strategy we looked at repeatedly divided the segments into two parts. For this challenge, I want you guys to modify the previous code example to return the minimum value in a list while doing a three-way search instead of a two-way search. For example, in the list here, we divide the 9 elements into 3 segments of length 3, and then we further divide up those segments into 3 more segments of length 1 each. We can then find the minimum value of the whole list based on the method of splitting the same way we did previously. So before you guys go ahead and try and implement this, I want to give you all a hint. In the two-way split example, we split the segment in half based on a single midpoint. Now we want to split the segment into 3 parts, which means that we will need 2 midpoints instead of a single midpoint. Alright, I'm going to give you guys a moment to pause the video if you want to give us a try. I'm going to reveal the solution in the next slide. Awesome, I hope you guys were able to give that a try, and here's one way to implement the 3-way split using the divide and conquer strategy we just talked about. So rather than having a single base case, I address 3 different base cases when the size of the interval is 3 or smaller. In these cases, simply return the minimum of the existing values. This approach simplifies handling the scenarios where the interval consists of precisely 3 elements or cannot be divided any further. If none of these base cases are encountered, we know that our interval comprises of 4 or more elements. When the interval is 4 or more elements, we can split the current interval into 3 segments. Since we want 3 separate segments, there has to be 2 different midpoints by which we can split across. These midpoints can be found at the 1/3 mark and at the 2/3 mark. Once we have our midpoints, we can then split the current segment into roughly equal thirds and return the minimum value found in the list. Awesome, guys. That's all I have for now on divide and conquer. In the next videos, we'll be taking a look at merge sort and binary search, both of which use the divide and conquer paradigm as a central component to the solution. Thanks again for watching. Please like and subscribe, and I'll catch you in the next one. Cheers.